So hopefully you have some of those visuals written down where you can picture what the first and the second, or what the positive and negative concavities look like. All right, so we define a function as being concave up when f double prime of x is greater than 0, and we describe a function as being concave down anytime f double prime is less than 0. And then we have that point of inflection. And the point of inflection is two things. It is when f double prime of x, well, the only option I haven't covered is what? Equal to 0, but also one that's commonly forgotten is the undefined again. When it's either equal to 0 or undefined, and it's not just enough to say it's undefined, and the second derivative analytics, so making a chart like we did before, reveals a change in concavity. We talked about that when we were doing first derivative. It's all about the change. Think about Meghan Trainor's song, right? It's all about the base. It's all about the change here. Okay, if you don't have a change, it does not count as an extreme value or a point of inflection. You have to mention the change to get credit for identifying what it is. So let's apply this to some functions. Let's look at the function x cubed minus 2x cubed, I forgot the lead coefficient, x squared plus 22x minus 5. And we're going to do this second derivative analytics, but we're going to do it with in conjunction with the first derivative. So we're going to find our first derivative. First derivative will be 6x to the second minus 28x plus 22. In factored form, I can pull a 2 out of that. That's going to leave me with 3x squared minus 14x plus 11. I would set that equal to both 0 and undefined. Okay, this factors. Hey. Morning. Okay, so we've got factors into 3x and x, and factors into negative 11 and 1. I should be really dutiful and set it equal to undefined also. But we know that when we set a polynomial equal to undefined, there are no corners or cusps or vertical tangents for a cubic, so that won't produce anything new. So I'm going to have critical points at x equals 11/3 and at x equals 1. So those are my two critical values. Before I make my chart, I want to move on to the second one. So we're adding another layer to this function. So now we'll take the second derivative. Second derivative will be 12x minus 28. And it's pretty easy to set that equal to 0. And I should set it equal to undefined just for practice as well. But that doesn't produce anything new. So we're going to have x equals 28 over 12, which is 7 over 3. So these are all my important numbers. My domain is all real numbers. My interval now is going to not just be 1 and 11/3, but it's also going to include 7/3. And so as I set up my interval, I got to think about these numbers in order. So it's going to be x less than 1. It'll be between 1 and 7/3. It'll be between 7/3 and 11/3. And then it will be greater than 11/3. So we're going to add a couple things to this, 2 lines that we didn't have before. All right. So we're going to have f prime of x to check and what it means, and what it means about f of x. And we're going to have f double prime of x to check and what that means. I guess I made mine too long. So you're just adding this. Again, this is like scratch work. It's not going to be part of your final answer. It's just what you're doing to prepare for what you're going to write. Don't need those quite that long. So I just got to pick some numbers that are within my interval and then check them in the first and the second derivatives. So I'm going to pick a number that's less than 1. The easiest number for me to pick is 0. And I am going to now check the value of 0 in both the first and the second. Make sure you're plugging it into the right place. So when I pick 0, I'm going to plug it into the first derivative. That's going to give me a positive number. And I'm going to plug 0 into the second derivative, and that will give me a negative number. So what that tells me about this function is that it is increasing and it's concave down. It is increasing and concave down. So sometimes it helps me, right underneath it, I just kind of draw that. What does it look like when it's increasing and concave down? And I kind of think, okay, that's a section that looks like that. That's increasing and concave down. So I'm going to connect that to whatever's coming next. Okay, Rebecca, pick me a number between 1 and 7/3. 2, okay. Let's put 2 into the first and second derivative. So if I put 2 in, and you can use your calculator if you want to. All right, plug 2 into the first derivatives. That'll be 6 times 2 squared, which is 24. Minus 28 times 2, that's minus 56, and then plus 22. So I've got 48 minus 56 altogether. What's the overall value going to be of that? Yeah, it's going to be negative. All right, so that tells me it's going to be decreasing. And then I want to take that same number 2 and I want to test it in the second derivative. So I'm going to plug that in right here. And plug the number 2 in there. That's 2 times 12, which is 24, minus 28. That's also negative. And so I've got concave down again. And so the next section of my graph is going to be decreasing and concave down. So that'll be the section that looks like that. That's what decreasing and concave down looks like. And eventually we'll make this continuous. And we just keep doing this for each one. Okay, let's see. Terry, can you pick me a number in the next interval? Something between 7/3 and 11/3. 3. Okay, great choice. All right, so we'll take the number 3 and we're going to test it in our first and second derivative. So we'll take the number 3 and we're going to plug 6 times 3 squared minus 28 times 3. So let's see, 6 times 3 squared is 9 plus, let's see, 54 plus 22. So that's 76 minus 28 times 3. That's 84. That's going to be negative again. So we've got decreasing. And we'll take the number 3, and we're going to put that into our second derivative. That's going to give me a positive number. So now I know for the first time I've got concave up. And so I need a decreasing piece that's concave up. And so it needs to be going down, but it needs to be bending in a way that it's going to be concave up. And so again, we'll make that continuous as we connect all these pieces together. And then we'll pick something that's greater than 11/3, the number 10, or something really nice and easy that we could do. Okay, if we put the number 10 into our first derivative, 6 times 10 squared is 600, minus 28 times 10, that's minus 280, plus 22, that's clearly going to be positive, so that'll be an increasing section. And then number 10 in the second derivative will also be positive, so that will be concave up. So now I have an increasing section that is concave up. And so when we join all of that together, remembering that this is a all real number function, so my overall graph is going to, follow that shape with arrows that increase and decrease. So now I know where I've got a point of inflection. Points of inflection only happen where there's a change from positive to negative. So I'm going to have an inflection point right here between that negative and positive. And then I also can identify that I'm going to have a max between that negative and positive, and then I'm going to have a min between that. Both of those are local or relative maxes and mins because this function does have all real numbers as its domain, and the inflection point is at 7/3. So if you're practicing what we did yesterday in terms of writing a sentence, you have to say the word change when you're talking about inflection. So it would be something like this. The function f of x has an inflection point at x equals 7/3, and I don't know what the y value is. I'm sorry, I didn't look that up ahead of time, but we would find the y value because, and then your because always has to be based on the second derivative, because f double prime changes from blank to blank, and in this situation it's changing from negative to positive, which means f of x changes from concavity. Okay, it changes concavity from down to up. Okay, so that's a sample of how you would write that. You have to mention the change. Again, that's just going to be the most important point there. All right, any questions so far? It's very similar to what you did before. You're just doing another layer of it. So let's do one more example. And we're going to do this to an exponential function. So we're going to do this to f of x equals e to the negative x squared. So we're going to perform first and second derivative analytics on that to figure out what's going on. So f prime, we're going to do the first derivative, so that's e to the negative x squared, times the natural log of e, times the chain rule, which is negative 2x. So to clean that up, that would be negative 2x times e to the negative x squared. And I would set that both equal to, in fact, I would probably write that with not a negative exponent. So I'd have negative 2x over e to the positive x squared. So I'm going to take that and I'm going to set it equal to both 0 and undefined. So equal to 0 over 1. And the same equation equal to undefined. And I would solve for some critical values. So we'll cross multiply. So negative 2x equals 0, so x does equal 0. That's one of my critical points. When I cross multiply the other way, I get e to the x squared equals 0. And there are no critical points that come from an exponential being equal to 0. So I have my first critical point. Then I need to do the second derivative. You could use quotient rule to do the second derivative, or you could use product rule to do the second derivative. If you use this form circled in yellow, then you would apply the quotient rule, QR, okay, quotient rule. If you do it this way, applied in green, then you can do the product rule. I'm more of a fan of the product rule than the quotient rule, so I'm going to do it that way. So my second derivative, my product rule says, all right, I'm going to start with e to the negative x squared, and I'm going to multiply that by the derivative of negative 2x, which is negative 2, plus negative 2x times the derivative of e to the negative 2x, which again is e to the negative x squared, e to the negative x squared times the natural log of e times another negative 2x. So we want to clean that up. So my lead term will be negative 2 e to the negative x squared plus, because I've got a double negative going on there, 4x squared times e to the negative x squared. And so I would factor out what that has in common. So I'm going to take out, I can take out 2, and I can take out an e to the negative x squared. That's going to leave me with negative 1 plus 2x squared. Or negative 1 plus 2x squared over 2 e to the negative x squared. So again, I'm going to always encourage you to write it without any, yeah?
e to the positive x squared?
Yeah, thanks. I was just going to say, I'm going to encourage you to write it without negative exponents, which, all right, then you're going to set that equal to 0 and undefined. Yeah.
Wouldn't 2 still be up over there?
Wouldn't 2, oh, yeah. My 2 is in the numerator. Okay, so 2 parentheses, negative 1 plus 2x squared over e to the x squared set equal to 0 over 1. And again, to negative 1 over, to 1 over 0. And we'll do our cross multiplying. The idea is, oh, that's right, we're on extended lunch today. So you'll cross multiply, and you'll come up with your critical points. We're not going to get anything on the undefined side. And the other one should solve. Divide both sides by 2. Add 1 to both sides. So 2x squared equals 1. So x squared equals half. And so x is the plus or minus square root of 1/2. So then you're going to make your chart. You're going to use the 0 from the top, the first critical point, and you'll use these two, and you'll make your chart to find out if it's increasing, decreasing, concave up, or concave down.